All right. Hello, everyone. This is Nathan here, and we are going to be talking today about problem number 7. So, problem 7, we're trying to find the strength of magnetic field that we need to collect a proton that is being accelerated through a capacitor and moving into this area of magnetic field. Um, and we're looking specifically for how strong the magnetic field needs to be so that it ends up down here 10 centimeters away after moving into the magnetic field. And so first we have it being accelerated through our capacitor, and then once it gets into this region of magnetic field, it will have some velocity right here, and that's going to stay constant, and we're going to enter what's known as cyclotronic motion. And at that point, basically, since we're in a magnetic field, the force acting on the particle is always going to be perpendicular to the magnetic field and the velocity, meaning basically since our particle is moving this direction and our magnetic field is going straight in and out of the page, that it's going to be moving towards the center of this circle right here. So this particle will actually move in a circular fashion. So that's what allows us to find out the field here, or the field strength, because we're going to treat this as if it's a circle of radius 5 centimeters because our diameter was 10 centimeters.
Okay, so the trick then is understanding that this is the cyclotronic motion, and the equation that we use is on the equation sheet, and it is R equals mv over qb. M and Q have to deal with the mass and the charge of our particle, in this case the proton. So both the M and the Q. V is the velocity, and then of course B is the magnetic field, and that's what we're trying to find. So we'll go through and solve for B from that equation, and then also realize that we've got to know what the velocity is. So in this case, we just used a simple energy balance. Potential energy on one side, kinetic energy on the other, and found out, and solved for that velocity. Plug that in until we get our symbolic solution that you see there. And again, M is the mass of the proton, E, and then we just replace that with Q. So that's E, that's the 1.6 times 10 to the negative 19th. So at that point, it's the plug and chug. We're putting the numbers in because we have all of those values.
Yep. And so you see we plug our numbers in here and plug in our mass, our charge, our radius, which we've converted into meters for sake of units. And then again over here, E. And the change in voltage for our potential energy here, since we're going from positive 50 to negative 50 volts, we actually have a potential difference of 100 volts. That's where that comes from right there. And of course, the mass of a proton again. And when we compute this, we get that our magnetic field strength is 0.0289 Teslas. And over here we have some unit analysis, a little bit of a weird unit, but it does actually work out. Okay, all right, and that's it.